here we go. This is going to be my last problem for a little while. This is 2015 BC International, question number 4. Still calculator inactive. In a national park, the population of mountain lions grows over time. Okay. At time t equals 0, where t is measured in years, the population is found to be 20 lions. In part A, we're told that one zoologist suggests a population model P that satisfies the differential equation dp dt equals 1/4 times the quantity 220 minus p. We're asked to use separation of variables to solve the differential equation for p with the initial condition p of 0 equals 20. Okay, so dp dt is equal to 1/4 220 minus p, and we have the initial condition p of 0 is equal to 20. We know that we need to use separation of variables, so I'm going to multiply both sides by dt. dp is 1/4 of 220 minus p times dt. I need to separate the variables using legal algebra. I see the dp over here. I see this part on the right-hand side that involves the p. So I'm going to divide both sides by 220 minus p. Now I'm going to leave the 1/4 on the right-hand side. If you wanted to, you could definitely divide by 1/4 over onto the left, but that is just going to be a major pain in the butt. So we're going to integrate both sides now. Well, let's keep going. The integral on the left, what's the integral of 1/4 with respect to t? Be careful, this is 1/4 t plus your constant of integration. Now, the integral on the left, you might not recognize right away what to do. So let's see, what could we do? We can rewrite as 1 over 220 minus p dp. You're probably thinking, because of the 1 over, that this is going to be something involving the natural log. You're correct, but you've got to be careful here. It's going to be the natural log of 220 minus p, but it's the negative of that. Now you might want to stop and think about this for a bit. Why the negative? If this is the antiderivative, when you take the derivative, you need to get back to 1 over 220 minus p. If you just took the derivative of natural log of 220 minus p, you'd have 1 over 220 minus p times the derivative of the inside, which is -1. You'd have the negative of what you're looking for. By introducing this other negative, you're going to get the positive, which is what you want. So negative natural log absolute value of 220 minus p equals 1/4 t plus c. Now it's totally your choice how you want to go about doing this. You could solve for p first, then use the initial condition, or use the initial condition first, then solve for p. It really doesn't matter. I'm going to use the initial condition first. I've really started to like that over the last couple of years. So let t equal 0, let p equal 20. You get negative natural log absolute value of 220 minus p, 220 minus t is equal to 1/4 times 0 plus c. Negative natural log of 200 is equal to c. Great, that's c. So now we have negative natural log absolute value of 220 minus p is equal to 1/4 of t minus the natural log of 200. Now what's your goal? Your goal now is to solve for p. So we're going to multiply both sides by the negative. Natural log absolute value of 220 minus p is equal to negative 1/4 of t plus the natural log of 200. I'm still trying to get p by itself. To get rid of the natural log, we exponentiate both sides. And we do that because when you have e to the natural log of stuff, the e and the ln are inverses of each other, and you get the absolute value of 220 minus p. Now this is e to the negative 1/4 t plus the natural log of 200. And I want to be careful here. You might be tempted to cancel out the e and the ln here, but you really need to do another step. This is really e to the negative 1/4 t times e to the natural log of 200. When the bases are the same and you're multiplying, You add the exponents together. The reason you do that is because e to the natural log of 200, as we mentioned already, the e and the ln are inverses, and what you get is e to the negative 1/4 t times 200. So where are we? The absolute value of 220 minus p equals 200 e to the negative 1/4 t. Still trying to solve for p. We have to remove those absolute values. 220 minus p is equal to plus or minus 200 e to the negative 1/4 of t. Now, using the initial condition, we know that at time 0, the population has to be 20. That's only going to happen if we go with the positive version here. So 220 minus p equals 200 e to the negative 1/4 t. Solving for p, I can subtract 220 to the other side. I can then multiply everything by the negative to get 220 minus 200 e to the negative 1/4 t. Now, if you're being raised well in the world of differential equations, you know to also look for domain restrictions. If I look at my final answer here, I don't have any restrictions on t. I'm not dividing by 0. I'm not trying to take a square root of a negative number. So no domain restrictions here. The t is not even a part, really, of the initial differential equation. No domain restrictions there. The only domain restriction comes in the very beginning of the problem, where you're being told that you are measuring since time t equals 0. So the appropriate domain restriction would be to say that t has to be greater than or equal to 0. And again, the College Board, you heard this probably in the AB videos, the College Board is not too worried when it comes to free response with the domain restriction. So if you forget to include it, you're okay. If you include it and it's wrong, probably going to be okay. Let's look at how points are awarded. When you reach the point and you have separated the variables, that was back here before integrating, 1 point, and this is an important place. If you incorrectly separate the variables, you lose this point and you cannot earn any more points after that. So that's huge. The next point is earned when you integrate both sides correctly. You have to get this side and that side, both of them correct. A third point for the constant of integration. Remember earlier when I said let's use the initial condition early and solve for c? That gets you a point, and that's one of the reasons why I like doing this, so using the initial condition early. And then your final point is for coming up with the domain restriction and solving for p. This is a total of 5 points. Separation of variables tends to be one of the highest, in terms of opportunities to earn points, one of the best places. That's part A. Not too bad, especially for a Calculus BC student. I'd expect really high scoring points here. Let's look at part B. In part B, we have a second zoologist suggest the population model Q that satisfies the relationship dq dt equals 1 over 500 times Q times the quantity 220 minus Q. Find the value of dq dt at the time when Q grows most rapidly. Well, what's going on here? This dq dt equals 1 over 500 Q times 220 minus Q, I hope you recognize as the logistic growth model. Depending on how you studied this, you may have learned this as dp dt equals k times p times L minus p, where L is your limiting population. So I'm not sure what's going on here with the zooming in and zooming out. Where L is your limiting population or your carrying capacity. Basically, L is the maximum population you could ever have. So in this case, for part B, Our L value is 220. When you studied logistic growth, one of the things that you should have studied is that the population is growing fastest. dq dt is a maximum at 1/2 the carrying capacity. So dq dt is greatest at p equals 220 divided by 2, which is 110. In part B, they want to know, find the value of dq dt when q grows most quickly. dq dt at q equals 110. We're going to plug into our logistic growth model. 1 over 500 times 110 times 220 minus 110. And there is absolutely no reason to even consider simplifying. This is what you needed. If you want to simplify, you're going to get to 121 over 5, but that's just foolish. So you earn 1 point for knowing that 110 is the population that you're interested in. And then you earn the second point for the plug-in, the evaluation, which can stop right here. And that earns you 2 points. Not too bad. All right, here we go. Part C. For the population model Q introduced in Part B, use Euler's method starting at t equals 0 with 2 steps of equal size to approximate Q of 10. So we know that dq dt is equal to 1 over 500 times Q times 220 minus Q. Euler's method, we're going to start at t equals 0, and we need to get to t equals 10 with 2 steps of equal size. So we're going to stop off at time t equals 5. The process with Euler's method is a pretty standard one. We're going to find the slope, so we're going to find dq dt at t equals 0. Well, all right, that's 1 over 500. Now wait a second, t is equal to 0. What's q? Q is your population at time 0, and we were told earlier that the population was going to be 20 times 220 minus 20. This is the slope. Now unfortunately you are going to have to do some work here. So we've got 20 times 200. We can cancel out some zeros here. 20 times 2 is 40. 40 divided by 5 is 8. That 8 is your slope. That means that your first tangent line is going to be 8 times t minus 0 plus t minus 0 plus 20. You're going to use that to approximate the population at time 5. So that's going to be 8 times 5 minus 0 plus 20. 5 minus 0 is 5, times 8 is 40, 60. That's your approximation for the number of mountain lines at time t equals 5. To go further, you need to now find the slope at time t equals 5, which is going to be 1 over 500 times your new population of 60 times 220 minus 60. So that's 1 over 500 times 60 times 160. Again, we can cancel out some zeros here. 6 times 16 is 96 over 5. That's your slope. With that slope, you're going to find your second tangent line. So 96 over 5 times t minus 5 plus 60. You're then going to use that to approximate the population at time 10. Population at times 10 is 96 over 5 times 10 minus 5 plus 60. 10 minus 5 is 5. 96 over 5 times 5 is 96. 96 plus 60 is 156. The 156 is your final stop. It's your approximation for the population at time t equals 10. Nice job. Now, in terms of awarding points, they say 1 point for Euler's method with 2 steps. So what exactly does that mean? It means that you went through this process and you get 1 point. Maybe you made some computational mistakes along the way. Maybe you went from t equals 0 to t equals 6. I think that's crazy, but maybe that's what you did. And then 1 point for the final numerical answer. Now, if you're looking for where is the safe stop in this process, right here is your safe stop. At 96 over 5 times 10 minus 5 plus 60, you're done. You've locked in your second point. No more to do. Congratulations.